Hello students, in the previous class we have discussed about the applications of OpAmp, which are wave shaping circuit with the help of integrator as well as differentiator. And in this lecture we are going to discuss about the on-off controller using comparator or Midtrigger. So first of all we should know what is an comparator. So comparator is a circuit which compares the input signal voltage on one input of an OpAmp with the unknown voltage known as a reference signal. Okay, so basically what we are going to have in this comparator is going, as its name indicate, it is going to compare the two things. Now which are the two things? See, out of two input terminal, one terminal is connected to the ground, second terminal is having some sort of input signal, and that input signal is compared with some reference signal, and the entire working of this circuit is called as a comparator circuit. Okay, so this is how, as you can see, the comparator circuit looks like. The first thing is that obviously it have two inputs, inverting, non-inverting terminals. Secondly, there is a VCC plus VCC and minus VCC, pin number 7 and 4, and at pin number 6 we have an output. Simple as that. So now we will study how to use this comparator for turning on and off the circuit. Now just say this is nothing but a diagram of voltage comparator. Now voltage comparator is what? Here we have input voltage at one terminal, reference voltage at other terminal, supply plus VCC minus VCC, and output VO. Correct. So this is an open loop comparator circuit. Now what is open loop? Without any feedback. If we are having feedback, that is closed loop. If you don't have any feedback, then we can call it as a open loop comparator. Okay, so it is connected in which a known reference value or known reference voltage is applied at the inverting input. Okay, and the time varying signal is applied at Vin. As we can see in the diagram, this reference voltage is applied at the non-inverting terminal, and this input quantity, we know the value of this input, and that is applied at the inverting terminal. So since the Vin is connected to the non-inverting input at op-amp, so it's so that this type of circuit is referred as a non-inverting comparator. Okay, and if we are applying input at the inverting terminal, then we can call it as a inverting comparator. A typical non-inverting comparator figure is shown in the following figure. So typically how your network comparator looks like is shown in the following figure. Now see, in this figure, for to the non-inverting terminal, we have input V in. The inverting terminal is connected to the ground, again supply and output voltage. Now the non-inverting comparator is connected in open loop condition. Now I have just told you what is open loop, without any feedback. Now here in this diagram we don't have any kind of feedback. That is why we can say that this configuration is of open loop configuration. That is, we don't need any feedback to operate the operational amplifier. The op-amp is operating in a saturation region. The inverting terminal is connected to the ground. Hence, the reference voltage comes ground potential for this comparator. So, in this case, what is your reference voltage? Reference voltage is set to the 0, and to the other terminal, to the non-inverting terminal, we have applied the input signal. So, what is going to happen? Whatever input signal you are going to apply, that will get compared with the 0 volt signal, because at inverting terminal we have applied a 0 volt. The comparator compares the input voltage V in with the ground potential and indicates as the output by the output voltage level whether the input signal is positive or negative. So to understand this working of non-inverting comparator, let's study the following diagram. By studying this diagram, we will be able to understand the working of non-inverting comparator circuit. This is the transfer characteristics of comparator. From the above figure, like we can see that the transfer characteristics are, as long as Vin is positive, the output voltage is positive. See, to the input of comparator, you are going to apply this kind of input voltage. Correct? So this is positive half cycle, this is negative half cycle. So whenever, like, as long as your input voltage is the positive, what is going to happen to the output? Your output is plus Vsat. Now what is plus Vsat? It is plus saturation voltage, positive saturation voltage, and minus Vsat is negative saturation voltage. This is your input and this is your output. Sorry, this is your positive input and this is your negative input. So the thing is that as long as your input is positive, your output of op-amp is plus Vsat. Okay, the output is at positive saturation voltage. But when Vin becomes negative, if your input becomes negative, the output is suddenly drop to the minus V saturation. The switching of V out from plus V sat to minus V sat or vice versa occurs when the input voltage V in crosses the zero level. So initially the thing is that we are studying the comparator circuit. Comparator is going to compare two different things. Which are the two things? First one is your input signal, whichever you applied, and that signal is going to get compared with the 0 volt signal. So as soon as your input voltage crosses the zero level, your comparator is start going to give the outputs. So what is going to happen? As soon as the inputs crosses zero, the first thing is you will have is a positive half cycle. For positive half cycle, your output is plus V sat, and after positive half cycle we have negative half cycle. For negative, your output is minus V sat. So this process is going to remain continue process, and that is why we can just call this circuit as, like, we can use this circuit to detect when the input signal crosses zero level or not. Okay, for the detection of input, whether your input is crossing zero level or not, we can use this circuit. And because of the performance of the circuit, it is also called as a zero crossing detector. Okay, why we call this as a zero crossing detector? Because it is used to check whether your input signal crossing zero level or not. Okay, so for example, V reference is 2 volt. In the figure, if we applied this reference voltage, instead of connecting it to the ground, we have applied it is of 2 volt. Okay, now the input voltage as sine wave is applied. So we have applied reference as 2 volt and we have applied input as a sine wave. So there is a power supply of plus minus 10 volt connected to the plus VCC and minus plus VE. As long as V in is less than the reference voltage, so here we have applied reference voltage as 2 volt. Until and unless your voltage is less than 2 volt, your output of the comparator, whatever the output you're going to get at the comparator, that output will remain low. Okay, or that will be near about minus 10 volt. Okay, as soon as your input voltage crosses the 2 volt. What is 2 volt? It is a reference voltage. So as soon as your input crosses 2 volt, in that case what will happen? Suddenly your output will shift from minus 10 to plus 10. Why? Because it is a reference voltage, it is a power supply. Okay, thus the high at output of operational amplifier indicates the input signal is greater than 2 volt. Whenever we receive high voltage at the output of comparator, we can say that the input voltage is crossing 2 volt. With using IC741, we can illustrate with the example to show how OpAmp can be used as a comparator to drive LED. So if you want to drive an LED, how OpAmp can be used? See, here we are using a fixed potential divider. What is potential divider? It is a simple voltage divider circuit where you will get the voltage at this node point. Okay, and that node point is connected to the non-inverting terminal of an amplifier, operational amplifier. To the non-inverting terminal, we have applied our input signal. So these two signals are continuously get compared with each other, and whenever your input signal is greater than your reference signal, your output of your comparator will be on, and you will get some voltage across LED and your LED will turn on. Okay, so what is the difference between these two figures? Here, in case of first figure, input is applied to the non-inverting terminal. Here, input is applied to the non-inverting terminal. Okay, so this is what is the difference between two diagrams. Input is applied to the non-inverting terminal. Here, input is applied to the inverting terminal. Okay, so this is what is the op-amp, how we can use op-amp as a comparator, right? So up next we have to study this mid-trigger. Now what is mid-trigger? In the basic comparator circuit, feedback is not used. Now we have seen in comparator there was like the circuit connection was an open loop connection, and open loop means what? There is no feedback connected. But op-amp is if we use op-amp in an open loop mode, the gain of op-amp in an open loop condition is very high, or it is very large. So that what is going to happen because of the large voltage gain? So a small noise signal, like if you're not applying any kind of input, but because of there is small noise signal which is present at the input side, the op-amp is going to amplify, or op-amp is going to process that noise also. Okay, this create a problem. See, without input, your op-amp should not do anything. But as your open loop gain of op-amp is very high, it is going to amplify a noise signal also, and that creates a problem. So If we want to remove this problem, such unwanted noise cause an output to jump between high and low state. So if you are not using any kind of input, your op-amp should not jump between high state to low state or low state to high state, but still it is doing. Why? Because it offers a very high voltage, open loop voltage gain, right? And the comparator circuit used to avoid such unwanted triggering is called as a regenerative or Smith trigger, which uses a positive feedback. Now see, the thing is that in case of comparator, you are not having any kind of feedback. That is, comparator is used in an open loop configuration. We know the open loop gain of amplifier is very, very, very high. So for the very small noise signal, your op-amp is going to process that noise signal, and it will, output of that op-amp will jump between high to low or low to high, and this will cause a trouble in your output, right? And to avoid this, we are using a circuit which is oftenly called as a regenerative or Smith trigger. Okay, and this type of circuit, a regenerative circuit or Smith trigger, is using a positive kind of feedback. Okay, now we will see how what is positive feedback and how the circuit works. So have a look at the diagram. So this is what is your general comparator, it having two terminals, negative and positive supply output. But just look at this. What is feedback? The first thing is that feedback is small portion of output is fed back to the input. So we are taking some sort of output and we are giving it to the input. Okay, little portion of output is taken and it is given back to the input. That is called as a feedback. Now here we are using a positive feedback. Now this circuit is also called as an inverting Smith trigger because input is applied to the inverting input. Now we can just easily see the input is applied to the inverting terminal. Okay, it produces opposite polarity output. Now we know the property of op-amp. If we apply 1 volt signal at inverting terminal, it is going to produce the minus 1 volt of signal, right? So when Vin is slightly positive than reference voltage, what is going to happen? See, input voltage is slightly greater than your reference voltage. The output gets driven into the negative saturation. It is minus V saturation. Okay. And when Vin becomes more negative than V reference, the output driven in the positive saturation. So you have to understand these two statements. Whenever we have input is slightly positive. So there are two conditions, input and reference. So whenever your input is positive than reference, then the output of your op-amp is in the negative saturation. Okay, and whenever your input is more negative than reference, then your op-amp is driven into the positive saturation mode. Okay, so the output voltage is always either plus V saturation or minus V saturation. The level of voltage where it change can be controlled by the resistors R1 and R2. So we can control this shifting from positive plus V set or minus V set with the help of R1 and R2 resistors. Thus, a reference voltage can be obtained by using a potential divider or voltage divider arrangements, and we can just write it as, see, the point at which we have to calculate the voltage, that point divided by addition of all the resistors which are connected in the series and into output. Okay, so this is a general formula of voltage divider. What is voltage divider? The resistor the value of resistor across which you are going to calculate the voltage, that resistor is R2, divided by addition of all the resistors which are connected in series into supply voltage. Okay, here supply is output voltage. In case of V0, whenever you have a positive reference voltage, your output is plus V sat. That is why instead of V out, I am going to write plus V saturation. Remaining things are going to remain constant. Okay, but whenever we have a negative reference voltage, in that case, what is the value of V0? It is minus V sat. Okay, so this is nothing but your expression for negative saturation. Okay, so plus V reference is for positive saturation when V out is equal to plus V sat. And what is minus V reference? It is V out when it is the negative saturation when your output voltage is negative saturation. And whatever this plus V sat we have, it is called as a upper threshold voltage. Okay, and it is denoted by VUT, upper threshold voltage. Okay, and in whenever we have V out is equal to minus V sat, it is called as a lower threshold voltage, and it is denoted by VLT, lower threshold voltage. Okay, So from the equation 5.18 and 5.90, because basically from these two equations, we can rewrite the equation as VUT is equal to, what is VUT? It is upper threshold voltage, and that is nothing but your reference, positive reference voltage. Correct. So positive reference voltage is plus V sat upon R1 plus R2 into R2. So I can just write plus V saturation or upper threshold voltage as plus V sat R2 divided by R1 plus R2. Similarly, for the negative saturation or minus V reference or lower threshold voltage, we can write minus V sat into R2 divided by R1 plus R2, minus V sat R2 divided by R1 plus R2. So this is how we can achieve the two equations for the upper threshold voltage as well as the lower threshold voltage. The output voltage remains in a given state until the input voltage exceeds the threshold voltage. So the condition which we have seen, that is going to remain constant until and unless your input voltage exceeds the threshold voltage. Okay, so the transfer characteristics of Smith trigger can be drawn as like this. Okay, so this graph is called as a hysteresis. All right, so the graph indicates that once the output changes its states, okay, which state, plus V sat to minus V sat or vice versa, it remains there indefinitely until the input voltage across the threshold voltage level. So basically what is going to happen, once you get plus V sat at output, it is going to remain plus V sat only until and unless your input voltage crosses the threshold voltage. Once your input voltage cross the threshold voltage, in that case only it output is going to change its value, and this is called as a hysteresis of Smith trigger. The difference between upper threshold voltage and lower threshold voltage is given by VUT minus VLT. So we already achieved the equation for VUT and VLT. Just substitute these values in this equation, VUT and VLT. So at last, after performing this calculation, we will get, see here, this minus minus will become plus. Okay, so ultimately we have to add this plus V sat is 2 V sat. Okay, R2 plus R2 is 2R2 divided by basis R1 plus R2. So this is nothing but the formula to calculate hysteresis of a Smith trigger. Okay, so this is all for today's lecture. We will discuss remaining things in the next lecture.